All right, let's dive into a concept that is, no joke, secretly running the modern world. I'm talking about everything from the music you stream to the AI on your phone. It's called a vector space, and it's kind of like the hidden language of all these systems.
I mean, that sounds a little crazy, right? How can one single idea from math be the foundation for so many completely different technologies? Well, that is exactly what we're going to unpack today. And the answer, you guessed it, is the vector space. So here's our game plan. We're going to start simple, with this idea of a black box. Then we'll uncover the two super simple rules that make these systems work. After that, we'll finally define what a vector space is, see how a vector can be way more than you think, and wrap up with why this abstract idea is maybe one of the most practical tools we've ever come up with. Let's get into it. Okay, to get started, you don't need any complicated math. Not at all. All we need is a really simple analogy, the black box. This is going to be our foundation for understanding how all these systems really work. So imagine any system as this kind of mysterious black box. You put something in, that's your input, and you get something out, your output. Here's the key. You don't actually need to know what's going on inside the box. You just watch the relationship between what goes in and what comes out.
And this isn't just some thought experiment, you know? This is really how engineers and scientists think about very real, very complex things. An electrical circuit, a pipeline that processes data, even a machine learning model. They can all be treated like a black box. The focus isn't on the guts inside, it's all about its behavior.
Now, some of these black boxes are special. They're not chaotic or random. They're actually incredibly predictable. They follow two very simple rules, and these rules are the secret to their power. This whole idea is called linearity.
These are the two golden rules. First up is scaling. It's simple. If you double the input, you double the output. If you cut the input in half, you get half the output. Makes sense, right? The second rule is additivity. If you put two different things in at the same time, the output is just what you'd get from each one, added together.
Let's make this a little more concrete. Say you have a system where input A gives you output C. Well, the scaling rule just means that if you put in twice as much A, you get out exactly twice as much C. It's perfectly predictable.
And what about additivity? Well, if input A gives you output C, and a different input B gives you output D, if you put A and B in together, a linear system will give you exactly C plus D. No weird side effects, no surprises. The outputs just add up.
And that's really it. Any black box, any system whatsoever that follows those two rules, scaling and additivity, we call that a linear system. And that predictability, that's its superpower. It's what lets us build and understand incredibly complex stuff. All right, so we've got the black box idea, and we've got the two rules of linearity. We actually have everything we need now to finally answer the big question, what on earth is a vector space? So here's the big reveal. A vector space is simply a collection of things. We call those things vectors, where those two rules, adding and scaling, always work perfectly. You can add any two vectors in the set, or scale one up or down, and the result you get is always another vector that's still inside that same collection. It's a completely self-contained, predictable little universe. You've probably seen a simple example of this your whole life. Think about coordinates on a 2D graph. If you take the vector 1, 2 and add it to 3, 4, you get 4, 6. That point is still on the graph. If you take 1, 2 and multiply it by 2, you get 2, 4, also on the graph. The system is closed. It obeys the rules. So, the collection of all possible 2D coordinates, that's a vector space. Now, this is where the idea really starts to get mind-bending, because the word vector means a lot more than just an arrow pointing in space. This is where the concept just blows wide open.
So what can be a vector? Well, pretty much anything, as long as you can define a way to add and scale them. A digital audio signal, yep, that's a vector. You can add two signals together to mix them or scale one to change its volume. A single row of data in a spreadsheet, that can be a vector too. You can even think of entire mathematical functions as vectors. This leap in thinking is what makes vector spaces so incredibly powerful.
Okay, I know this might all seem very abstract. You might be sitting there thinking, so what? Why does this matter? Well, it turns out that the abstraction is exactly where the power comes from. It's the whole point.
Think about it. Instead of coming up with one set of theories for audio signals and a totally different one for financial data and another for computer graphics, we can just study the one single underlying structure they all share, the vector space. By understanding the rules of this one abstract idea, we learn something about all of those different fields at the exact same time.
And this isn't just some neat theory.
This is the engine that runs our world. In machine learning, every piece of data is treated as a vector in some massive, high-dimensional space. In engineering, signals are vectors. And if you've ever played a video game, every movement, rotation, and scaling of a character is all thanks to the mathematics of vector spaces.
This quote just nails it. It feels backward, but it's true. By taking a step back from the messy details of one specific problem and looking at the abstract pattern underneath, we end up creating tools that are way more powerful and can be used everywhere.
And this slide, this just sums up the whole journey perfectly. In math, you start with sets, which basically just tell you what things exist. Then you have functions, which describe the connections between those things. But vector spaces, they do something so much deeper. They define the rules for how entire systems behave and scale. They are, basically, the language of systems themselves.
So the next time you see AI do something amazing, or just listen to a song, take a second, see if you can spot those rules of scaling and additivity working behind the scenes. Can you see that invisible but incredibly powerful structure of the vector space holding it all together?